Controlled environment plant production engineering technology education modules are developed and presented in collaboration by the Ohio State University, Rutgers University, and the University of Arizona, with support from USDA, NEFA through their Higher Education Challenge Grant program. In this module, we're going to continue our discussion on humidity management. This is part 2 of control. This module is presented by Dr. Peter Link, who's an associate professor of The Ohio State University. We will discuss 2 aspects of humidity control. By the end of this module, you will be able to relate humidity to disease control and plant growth, and also be able to describe the methods of controlling humidity. Water is necessary for plant growth, but water in wrong places in the greenhouse could cause concerns. Wet canopy promotes fungal spore germination. It causes diseases like powdery mildew, white rust, and botrytis. Extra water at wrong places of a greenhouse is a concern of disease control and plant growth. Splashing from condensate dripping spread bacterial diseases. Water puddles on greenhouse floors are warm beds of algal growth. As shortfly feeds on algae, and the shortflies are vectors of diseases, population of shortflies could help disease to spread, and that's undesirable for our greenhouse plant production. At the bottom left, we see a picture here. We see plenty of algal growth underneath the gutter. This is because the condensate was not properly drained and flowed down through the pipe and get the underneath area wet, and that provided a warm bed for the algal growth. The picture in the middle, we see this wet floor also has algal growth. On the bottom right, this walkway was overwatered, remained wet, which is not only a warm bed for algal growth, but also a safety concern for workers. Light loss due to condensate droplets on the greenhouse roofs is because condensate droplets reflect light and reduce light transmission for plant growth. At the bottom left picture here, we show droplets underneath the inside surface of glazing material. At the bottom right, we see the picture showing condensate formed in between 2 layers of double poly films. Condensate alone, if that is a thin layer of water, that's not going to have much effect on the light transmission. But when the droplet forms, then light will reflect off the surface of the droplet and cause less light to transmit through the glazing material, and the less light is available for plant to grow. On the bottom right picture here, it showed a lot of condensate formed on the inside surfaces of the 2 layers of the films. For growers using inside air, that's inside of a greenhouse space air, to inflate the double poly, it is more problematic, because greenhouse air is typically warmer and higher humidity. Pumping that air in between 2 layers results in larger amount of condensate. It is better to use outside air to inflate double poly. Outside air is typically cooler, but has less humidity, and less condensate will form. Humidity environment is very important for plant growth in a greenhouse. As we discussed in our first module on the humidity control, we introduced the concept of vapor pressure deficit. And vapor pressure deficit, or VPD, is a driver of transpiration. Transpiration affects water transport and nutrient uptake. Transpiration also affects photosynthesis because it effect on the gas exchanges. The gas exchanges include water vapor and also CO2. When the VPD is too high, the plant cannot keep up with the transpiration demand and drought stress occurs. Drought stress occurs when the rate of transpiration exceeds the rate at which water can be transported from the root to the leaves. We have discussed the importance of humidity management related to disease control and plant growth in a greenhouse environment. We're going to continue on to discuss what humidity targets are best for pest management and for plant growth purposes. For pest management, first thing we want to do is try to keep leaf surface dry. To do this, the plant temperature needs to be warmer than air dew point. And secondly, we want to prevent condensate from dripping onto a plant from overhead structures. And to prevent condensate forming on overhead structures, then the structure temperature needs to be warmer than the air dew point. And for plant growth, we want to optimize the amount of light transmitted through the glazing material. Thus, we want to minimize the amount of droplet of condensate that form on glazing material. And to do this, again, the glazing temperature should be warmer than the air dew point. And we also want to have the best VPD range for transpiration management, so the plant can be in an ideal environment for its gas exchanges for the highest photosynthetic efficiency. We have talked about the importance to have targets of VPD to provide the best environment for plant growth and disease control. So what are the targets appropriate for general greenhouse production? Before we look at this number, 0.45 kilopascal to 1.25 kilopascal range, I want to emphasize that each crop has different optimal VPD ranges. And here, what we discuss here is just a general rule of thumb. A general VPD range for a greenhouse is from 0.45 kilopascal to 1.25 kilopascal. And this is looking at higher limit when plant cannot meet the transpiration demand. And we're also going to look at lower limit when disease pressure becomes too great. For higher limit, we're looking at 1.5 kilopascal for the first stage of the pepper crop, for it may not be able to keep up with transpiration demand. And in this research, it is important to know that this is for a specific crop and for a specific growing stage. And for the lower limit, as that vapor pressure deficit reduces, there's a greater risk of disease. Research found that greater than 0.20 kilopascal is important to relieve the most damaging disease infections. At a higher vapor pressure deficit, it can reduce fungal pathogen activities at 0.43 kilopascal. So we look at the lower limit and we look at the higher limit, and that concludes a range of a VPD target for general crop production. Again, each crop will have a different VPD range. To maintain moisture level within the VPD range, in some situations we need to add moisture to the greenhouse environment. In some situations we need to reduce moisture level in a greenhouse. Since humidity reduction could be an energy-intensive operation, we are introducing 4 steps from the least energy-intensive to the most energy-intensive methods for reducing humidity. The least energy-intensive approach is simply grow dry. Just provide enough water to plants in time without leaching. That can reduce humidity level in the greenhouse. Second is to drain condensate. When there are condensate formed underneath a superstructure or underneath glazing, then simply drain it away. As long as condensate don't drip onto plants, then they have less effect on that disease pressure. Also, by draining away, we can also prevent light reflection of the condensate droplet. That's increase the light transmission that provides more light for plant growth. The third step is circulate air. Let us use the whole greenhouse volume to average out the humidity level. Wherever there are high humidity areas, using circulating air, we can spread it out so that humidity level in a greenhouse is evenly distributed. If all the three steps above still cannot bring the humidity level down to the desired moisture range, then we need to do dehumidification. This is generally a very energy intensive operation. We need to bring outside air in, heat it up, then purge moisture. Growing dry by not overwatering is the least expensive way of keeping greenhouse humidity low. Do precision watering. Make sure water is going where it is intended. Drip irrigation would be an ideal setup. Also, the timing of watering is important. For example, do not water just before sunset because the extra moisture carried into the night could present a problem. Drain condensate is the second least energy intensive operation for humidity reduction. When we see condensate form underneath a gutter, we can simply use a condensate drain to remove the condensate and keep it from dripping on the plant. And also, we can consider the glazing material service. There are commercially available spray-on material, the basic surfactant, that would reduce the surface tension and allow condensate to drain. Also, when we install double poly on a roof, we need to be careful not to form too many wrinkles, because the wrinkles, those can become the collection point of the condensate. For example, as shown in this slide, the wrinkles on the underneath film, those are excellent collection points, and that cause condensate to drip. In this case, the growers add another layer of plastic underneath to prevent dripping onto plants. But at the cost of collecting condensate, extra layer of plastic will further reduce light transmission. The third step for humidity reduction is to circulate air. By moving air inside the greenhouse, we can even out the moisture distribution. When we talk about circulating air, we need to look at both horizontal and vertical airflow. Horizontal airflow and vertical airflow are all important for even out the humidity distribution in the greenhouse. In this case, this bench with expanded metal that allows air to come in from the underneath and go out from the above. That would help to remove moisture within the canopy. And with the horizontal airflow fans, the shrouded fans has a deeper penetration and it is ideal for the plants with a denser canopy. Dehumidification is the most energy intensive step of the 4-step greenhouse humidity reduction procedure. This can be done by either purging high humidity air in the greenhouse and replacing it with dry air from outside, or it can be done by using dehumidifiers, either mechanical or chemical dehumidifiers. To purge high humid air in a greenhouse, this can be done by using a heat and vent operation. This operation can be implemented by setting heating and cooling set points close to each other. This will cause heating and cooling equipment to operate alternately without much delay in between. The disadvantage of this operation is that since there's only very small time delay in between the heating and venting operation, the heated air from the heating operation only has a very short time to absorb the moisture in the greenhouse. That said, vented warm air contains less water than what is canned. To improve the efficiency of that heat and vent operation, and a heat mix and vent operation is recommended. In this operation, there is an interlock in between heating and venting operations. A delay, for example 5 minutes, is designed to allow the warm air provided from the heating operation to have more time to absorb moisture in the greenhouse. That's when venting this heated greenhouse air, there's higher moisture level in the air. That's more moisture is purged. Timing of the dehumidification is also important. Most often this is done after sunset or shortly before sunrise. After sunset is because the plant is still transpiring into the night, and this is when the highest humidity greenhouse is going to get. And we want to reduce humidity going into the night so that humidity in the greenhouse remain low throughout the night. And the second timing for the dehumidification operation is shortly before sunrise. And the purpose of this operation is to reduce humidity and to increase vapor pressure deficit to wake up plants and ready for gas exchange and ready for photosynthesis. In the previous few slides, we talked about different methods of reducing greenhouse humidity. And we have learned that dehumidification is the most energy intensive step of the 4 possible approaches. Thus, the decision for starting a dehumidification process need to be careful. In an early spring day in Ohio, I went into the greenhouse, looked up, and I found the roof is full of condensate. This may be an indication for growers to start a dehumidification process. However, when I measured the temperature and the relative humidity at the canopy level, I found the microclimate around the canopy is about 25 degrees C and a 40% relative humidity. Is this condition cause for dehumidification? Let's look at the VPD of the air. This is a quick review of what we have learned about determining VPD from the previous module. Let's look at how we can determine the VPD of the air at a 25 degrees C and a 40% relative humidity. First, we find the temperature on the x-axis. It is 25 degrees, as shown in this red dot. Then we go up to the relative humidity, which is 40%. Then go across to determine the vapor pressure of the condition, 25 degrees C and 40% relative humidity. And we found that vapor pressure is 1.28 kilopascal. Then we find the vapor pressure at 100% relative humidity at the 25 degrees C. And we can find the vapor pressure of 3.27 kilopascal. Therefore, the vapor pressure difference between the two is 1.99 kilopascal. This vapor pressure deficit is in the range of 0.45 to 2.0 kilopascal range. For plant growth, the VPD is in a reasonable range, therefore there's no dehumidification should be required. So for this greenhouse, at 25 degrees C and 40% relative humidity, VPD is 1.99 kilopascal. That's appropriate range. No dehumidification is required. Then the question is, why there is so much condensate on the roof? This is because the dew point for 25 degrees C and 40% relative humidity is 10 degrees C. Remember, I mentioned to you that this picture was taken from an Ohio greenhouse in early spring. And outside temperature is about 0 degrees C or below. Therefore, the outside temperature is lower than the dew point that the condensate forms on the roof. To prevent dripping damage, the best approach is to drain away that condensate on the roof instead of dehumidification to further increase VPD that may damage plants and use a lot of energy. The best approach here, again, is to drain away the condensate. There are also situations when a greenhouse environment needs to have reduced VPD for better plant growth. And this can be achieved by either reduced air temperature, raise air humidity, or reduce plant temperature. There are many tools we can use to achieve the goal. First is to use shade curtain. By using shade curtain, we can reduce radiation load to the greenhouse and the leaf. Thus, we can reduce air temperature in the greenhouse and the plant temperature. Of course, by using shade curtain, we also going to reduce amount of light available for plant to grow. So this is a compromise between amount of light for plant growth and the heat load added to the greenhouse. Second method is using evaporative cooling, and we can either use fogging, misting, or wet cooling pad to achieve this. When we use fogging and misting, we should minimize time duration of water on plants or greenhouse floor. Just allow enough droplet to evaporate so that energy can be absorbed by water droplet, but without extended time duration on the floor that would cause algae growth, or extended time period of moisture on leaf surface that would cause fungal spores to germinate. Another method of soil heating. This method is appropriate especially for propagation area where warmer root zone and lower VPD combination is good for rooting and the healing of newly grafted plants. Let us use some exercises to review the humidity control discussion we have had so far. First, for plant production in controlled environments, name 3 important environmental moisture parameters. What are some of the moisture parameters we have discussed so far? Relative humidity, dew point, and vapor pressure deficit. Relative humidity is the most common environmental moisture parameter people use, and it is also the base of calculating VPD. Dew point is important because if air temperature is equal or below the dew point, condensate will form. Condensate can form on leaf surface and can also form on glazing surface or superstructure surface whenever the surface temperature is below dew point. VPD is important. It affects disease management as well as plants transpiration and gas exchange. Second question is, condensate forms on a surface when its temperature is lower or higher than dew point. this should be fairly obvious. When that surface temperature is lower than dew point, then condensate will form. Next question is, effects of lowering VPD on plants are: if outside environment has a lower VPD, then plants will decrease or increase transpiration. Lowered VPD will lower or increase transpiration. It will lower transpiration because of lower demand and lower negative force to help water molecule to move from the leaf surface to the air. Then when VPD is lowered, then the disease pressure will be lowered or raised. Lowered VPD will increase or decrease disease pressure. In this case, it's going to increase disease pressure because lowered VPD will bring plant surface closer to dew point, maybe even lower than dew point, and condensate may form that will help fungal spores to germinate. Thank you for viewing this teaching module. We hope to see you soon.